Okay, let's look at some of the effects that these intermolecular forces have on molecules and on some of the day-to-day things we see out in the world or in the lab. We're going to look today starting with surface tension, capillary action, and viscosity. So surface tension, what that is, when you have a liquid, once you get to the top of the liquid, the surface of it, especially if that's a water, an aqueous liquid, you'll see that you've got these water molecules, and due to hydrogen bonding, this water molecule is very strongly attracted to this one, and so you've got this kind of layer right at the surface, this two-dimensional layer of fairly strong hydrogen bonding, which makes the water not as susceptible for things to break through that surface. An example of that from the book, if you look at this fly here for trout fishing, you can see that it's not like floating in the water like you and I would float in the water. It's really on top of the water, and you can see the water is kind of bent down right here, and that's due to the surface tension. The fly does not have enough mass to actually break through the surface tension of the water, so those hydrogen bonds are still holding on, and they're just kind of like stretching the water a little bit instead of allowing the fly to break through. All right, there is also capillary action. And this happens because whenever you take glass is actually silicon and oxygen atoms bonded together, and glass is very polar. Well, water is also very polar, and so water molecules are very much attracted to glass. And we see that with two things. One is the capillary action, and the other is a meniscus. When you're in lab, you see that liquids have a meniscus with water, and that is due to this capillary action. Or excuse me, due to the water being very much attracted to the sides of the glass. And so normally when you look at water in a test tube, you will see the meniscus. The meniscus is the water at the edges being attracted to the glass. What happens if you make thinner and thinner tubes, because the water is so much attracted to the glass, because they are both polar, just like you have a meniscus, the water kind of comes up the edge of the glass, and due to surface tension, wanting to make the the surface area of the water as small as possible, it kind of sucks up the water a little bit, and the skinnier your tube is, the thinner the tube, the more the meniscus is going to go up, the more the surface tension is going to make the water creep up the tube. So when you have tall, skinny, long, skinny tubes, you find that all you have to do is touch the end of the skinny tube to an aqueous solution, and that solution will go up to the tube due to those intermolecular forces, due to the water being attracted to the glass of the tube, and also the surface tension trying to minimize the surface area of the water. So this is capillary action. Also note that in this picture here, this is water that has the meniscus this way. Glass is very polar. Mercury, this is liquid mercury in the tube. Liquid mercury is not polar. So its meniscus is opposite. Mercury does not like glass. Mercury is nonpolar, the glass is polar, they don't like each other, so the mercury is trying to get away from the glass. So you see in mercury, the meniscus looks upside down, because right here, in this corner here where the mercury is interacting with the glass, that's just not a favorable interaction. Mercury doesn't like the glass. They have different polarities, and so you get this type of situation with this upside down meniscus. Okay. And the last thing to look at in this little section is viscosity. And something to remember with viscosity, remember or get in your head, memorize the definition of viscosity. Viscosity is the resistance to flow. The higher the viscosity, the less it wants to flow. So syrup on a cold day is very, very viscous. It does not flow well. Honey is a very viscous liquid. It does not flow well. Water has very low viscosity. It flows really nicely. And this is due to the intermolecular forces. It turns out the stronger the intermolecular forces are, the more likely those liquid molecules are to adhere to each other, to want to be around each other, the less they just want to flow various places. The thing to remember is, though, is if you add heat, if you heat up a liquid, that lowers the viscosity. It makes it more runny. Perhaps you are a pancake or waffle aficionado, and you know that if you pour just cold syrup on your pancakes, that it flows very, very slowly. But if you stick that syrup in the microwave and heat it up, that hot syrup flows much more quickly. You heat up syrup, its viscosity goes down, its resistance to flow goes down, and that makes it flow much, much better. Okay. So the next thing we're going to look at is vapor pressure. And we already looked at this a bit in the thermodynamics chapter, but we are going to now add kind of the gas laws to our thermodynamics chapter. Recall vaporization, something going from the liquid form to the gas form. Well, think about the intermolecular forces. If something's going to a liquid to a gas form, the higher the intermolecular forces are, the higher temperature you need in order to break those intermolecular forces, the higher the boiling point. But what happens is if you have a container, say you have a container of water that is capped off here, you have liquid water in here, there's going to be gaseous water, water molecules in the gas phase above the liquid water. And so if you look at the partial pressure of water molecules in the gas phase, we call that the vapor pressure. So the vapor pressure is the partial pressure of that, whatever liquid you have in the container, the partial pressure of that liquid that's in the gas phase above the liquid, partial pressure of the liquid, of the molecules of the liquid that have escaped into the gas phase, that is the vapor pressure. And there's always a dynamic equilibrium between the liquid and the gas. If you're at equilibrium, liquid is always vaporizing to form the gas, but at the same rate, the gas is condensing back down to form the liquid. So, what this manifests itself is in terms of boiling point, because you know when something is boiling because you can see the bubbles. Now normally if we have a container with water in it, and if we're going to heat it up to get it to boil, usually the heat's at the bottom. That's the normal situation. And so you see bubbles coming up from the heat source, and that tells us that it's boiling. And we also know once it's boiling, its temperature does not change at that point. The question is, what's inside the bubbles? When water is boiling, what's inside those bubbles of boiling water? The answer is gaseous water, water in the gas phase. So if you look at your book, you will see this diagram here, where if you have water boiling, the heat's at the bottom, the bubbles are coming from the bottom. You see that if we magnify this area up, you'll see a whole bunch of water molecules in the liquid phase surrounding a whole bunch of water molecules in the gas phase. Well, the question is, what's the vapor pressure of these molecules in the gas phase? What is the pressure inside that bubble? Well, let's think about it. First question is, what is the pressure of the water molecules surrounding that bubble? Because we could probably think that if the pressure of the water molecules surrounding this bubble is higher than the vapor pressure, the pressure inside this bubble, then this bubble could never form, because all these molecules would just collapse that bubble back down again. They're at a higher pressure, and they will collapse a lower pressure bubble. So what this tells us is that the pressure inside this bubble has to at least be equal to the pressure of the water molecules outside the bubble. Next question. So here in this pot, we've got our liquid water in here. Here's our bubbles. We know the pressure inside the bubble has to be at least the same as the pressure of these water molecules outside. What is the pressure of the water molecules in the liquid phase outside of the bubble? Well, that's the same pressure as our atmosphere, 760 millimeters of mercury, 1 atmosphere. This means then, in order to get this liquid to boil, we must heat up this water such that the vapor pressure inside this bubble is 760 millimeters of mercury, the atmospheric pressure. Okay. So, when we look at water at room temperature, the normal vapor pressure of water at room temperature, 25 degrees Celsius, is only 23.3 millimeters of mercury. But what's the outside temperature? What's the what's the outside pressure? This is the vapor pressure of water, 23.3 millimeters of mercury at room temperature. What is atmospheric pressure? We remember that 760 millimeters of mercury, which means in order to get this liquid to boil, if we'd add heat, we'd have to get the vapor pressure up to 760 millimeters of mercury. We have to add enough heat to get the pressure up here to be 760 millimeters of mercury, then we can start boiling. And it turns out, in order to get that vapor pressure higher, we have to add so much heat to overcome those intermolecular forces. We have to heat it up to 100 degrees Celsius. Recall, water has hydrogen bonding, which is a particularly strong dipole-dipole force. That's why it takes a lot of heat. Now, this also means some other interesting things, especially if you live at high altitudes like Denver, which is 5,200 feet above sea level. As you go higher and higher in our atmosphere, the atmospheric pressure goes down. The higher you are above sea level, the less pressure you feel. Such that on an average day, the city of Denver only feels about 630 millimeters of mercury, not 760. What this means is how much heat you have to add to water to get this vapor pressure to be 630. Well, it takes less heat to get to 630 millimeters of mercury for vapor pressure compared to 760, which means water boils at a lower temperature. You don't have to add enough heat to get water to its vapor pressure. In fact, in Denver, water tends to boil at about 94 degrees Celsius instead of 100 degrees Celsius. And most of the time you don't really realize it too much. Maybe your ears pop a little bit. But where it really comes into play is if you're in Denver and you're cooking. Because things boil at lower temperatures. You might not have realized it, but when you're cooking pasta, you have to cook it for however long it says, 6-10 minutes in the boiling water, because it takes that long for water at that temperature to seep into the pasta and make it al dente. In Denver, it takes longer because the water's at a lower temperature. I'm assuming everyone's going to go on to Gen Chem 2 because chemistry is the most fascinating subject. And the second chapter in Gen Chem 2 is kinetics, how fast things occur. And we will find out that in general, the higher the temperature, the faster reactions occur. So the higher temperature, the faster that water is going to get into that pasta. In Denver, boiling water is not as high a temperature. It takes longer to cook pasta. It takes longer to bake cakes and things like that. All right. And this is actually these days given rise to a bold 1940s and 50s contraption, the pressure cookers. So if lowering the pressure means the water boils at a lower temperature, what would raising the pressure do? Yeah, you can cook in a pressure cooker where we don't have it open to the atmosphere. As you start generating the steam, as you start generating the vapors, the water vapor here, we don't let it escape, which means the pressure of the whole container gets larger, such that at your 100 degrees Celsius, because the pressure in here is so high, the water won't boil. And so you can keep adding more heat, and you can be cooking at 110 degrees Celsius before water starts to boil in a pressure cooker, which means it takes less time. All right. That's enough for this video. We will continue next time with a little math.